Okay, so now the centroid. So now you can copy that centroid thing.
Okay, wait a minute. You have this much room left.
Okay, I better make it short.
So was this last part, the equipolant systems, that's not going to be on the test?
Right, I mean, that's right. There's nothing about that by itself on the test, but that idea of moving the forces along their line of action is kind of an important thing to understand. Okay, so centroids. So the centroid is like the geometric center of an object. Center. You can do centroids in 2D or 3D. And we're going to use centroids for two things. I guess, well, yeah, we'll use centroid calculations for first finding the center of mass of odd-shaped objects. And then second, for problems with distributed loads. And so I'll go into each of these things like kind of on its own after I talk about how to calculate the centroid. The centroid definition is an integral definition. So the integral definition of a two-dimensional centroid says the total area of the body times the centroid of the body is equal to the integral over the area of the centroid of your individual increment of area times the increment of area. So I'll do like a little one of those integral drawings that hopefully I'll sort of explain how this works. In 3D, it's similar. It's essentially identical. So in that case, instead of an area, we're talking about a volume. And the volume times the three-dimensional centroid is equal to the integral over the volume times the centroid of each individual increment of volume times the increment of volume. Okay, so I'm going to use, to kind of illustrate how this integral definition works, I'm going to just do a calculation for a triangular shape, calculate the centroid of a triangle. So let's say that we have a triangle with just a generally, and let's say that it's a right triangle. Let's say that we have a general width B and a general height H. And let's put the coordinate system over here. and calculate where the centroid of this is. Okay, so if we're going to use this integral definition, and this is kind of true of integral problems in general, if you're using an integral formula to do any kind of calculation, the first thing you have to do is figure out how you're going to organize your increments. Okay, we're looking for little increments of area. So what's a good way to organize this? I mean, there's probably infinitely many ways to do it, right? Let's do it like this, just because it works out sort of nicely. So this is going to be a single increment of area. So this is dA. And what do we know about this area increment dA? Yeah, let's see. So what do we, I guess let's think about what we need for this increment. So for each increment, we need how much area we have, and that's this dA, and we need the x and y coordinates of the centroid of this strip, right? So where's the centroid of this strip? I mean, it's just the middle, the same way we've been doing for rectangular shapes up until now. So the centroid is here. Can we come up with coordinates for that point? Our x centroid is just going to be our x value, the x value of that strip. And what about the y centroid? Well, it's going to be half of the height of whatever that is, right? It's going to be how do I want to write this? So let's think about okay, so what do we know about the height for a given, so we're talking about this increment that's at a location x. What do we know about its height? Well, we know that its height follows the function of this line, right? And that line we can represent, because of where I chose the origin to be, as you can think of this as like the what do you call it? The y-intercept form is y equals h over b times x, right? So the centroid, the y centroid, is going to come from the line formula y equals h over b times x. If we just use this function, that would give us the height of this rectangle. So that's not exactly what we want, right? We want half of that, because we want the midpoint between y equals 0 and y equals this. So the centroid is equal to h x over 2b, halfway up, okay? And it looks like things are shaping up where we're going to be calculating everything in terms of x. So in terms of x, what's the area of this increment? The thickness is dx, and what's the height? The height is going to be the height of the rectangle. So you can think of it as y dx, which is hx over b dx, or h over b x dx. Okay, so now that we have, for each individual strip, the x centroid, the y centroid, and an expression for the area, we can just plug everything into this formula. So the area times the centroid is equal to the integral of, so what do we have for the formulas? The vector is, the x component is x, the y component is hx over 2b, and now we want to multiply that by dA, and dA is the area of that strip, which is hx over b times dx. And I'm going to multiply the hx over b through. This is just multiplying a vector times a scalar. So here we have hx squared over b. And here we have h squared x squared over 2b squared dx. What are the limits of this integration? Our x value is from here to here, so we're just going to integrate from 0 to b. And then I guess the last thing we have to do is calculate the area of that triangle. We can just use the triangle area formula. So that's just going to be bh over 2. Oops. And I'll rearrange it. So our centroid is going to be equal to 1 over the area. The area is bh over 2, so I guess I'll put the 2 up on top, times the integral from 0 to b hx squared over b h squared x squared over 2b squared dx. Okay, so how do we integrate a vector like this? How do I do this? I mean, really, I'm asking you. I've never seen this before. Yeah, that's right. We're just going to do it in 2 pieces. They're totally independent of each other. So, so I'll do the x component first. So the integral from 0 to b of hx squared over b dx, and I guess out here we have 2 over bh. So we can cancel this h with this h and pull out the b, and we have 2 over b times the integral x squared over b dx. No, I already pulled out the b. Okay, and so we get x cubed over 3 evaluated from 0 to b times 2 over b squared, and so we get b cubed over 3 divided by b squared, so we get 2b over 3. Right? I think that's right. So that is the x component of the centroid. And then the y component of the centroid we have 2 over bh times the integral from 0 to b of h squared x squared over 2b squared dx. One of these h's cancels with this h, and the 2 cancels with this 2. And so we have h, and I guess I'll pull all the constants out. So what we have left is h over b cubed, and inside the integral x squared dx. And so we have x cubed over 3 evaluated from 0 to b multiplied by h over b cubed. And so we have b cubed times h over 3b cubed. All the b cubeds, all the b's cancel, and we're just left with h over 3 is the y centroid. So that tells us that for a right triangle where the width is h, no, that would be weird. Let's make the width b and the height h. The centroid is 2/3 of the way from the point to the wall and 1/3 of the way up to the top. So this is 2b over 3, and this is h over 3. Okay. But now notice that we did this integral once and came up with a formula that we can use anytime we have a right triangle. Okay. That would be sort of tedious to do every time you had to do a distributed load or a center of mass calculation. But the good news is we did the integral once and found a formula that we can use for the centroid for any right triangle. So I chose my coordinate system to be over here to make the calculations a little easier, but I think the easiest way to think about it is that if you're always going, so with a right triangle, you always have, in either dimension, you have like a long side, a wall, and a point side. Okay, and you're always, to get to the centroid, going 1/3 of the way from the wall to the point. Okay, so this distance is width over 3, and this distance is height over 3. Okay, so for example, now if what if you had a right triangle like that? Where's the centroid of this? Let's say that this height is 5 and this is 2. Where's the centroid? And let's also, let's put the coordinate system up here. Well, we know that it's going to be a third of the way up towards the point and a third of the way over towards this point. So it's going to be right over here. This distance is going to be 5/3. This distance is going to be 2/3. And now we have to translate that into the coordinate system. So this point would be at 0, -5, right? And then you're adding to that 5/3. So is that what it is? Okay. So the y component would be -10/3. And then this one, we're going just in the positive x direction. So the x component is just going to be 2/3. Okay. So I wanted to do one example of an integral calculation, but really you're just going to be using these formulas. And the challenge, the only challenge to it, is making sure like these formulas are the figures that you're given are oriented a certain way. You sometimes have to sort of mentally turn it around backwards, turn it upside down, and then translate it into your coordinate system. Okay, so let me give you a few of these. Well, you know what? That triangle one I gave you in D2L, if you look under the course materials, yeah, there's a page that says centroids, and you're given formulas for a triangle, quarter, and semicircles. Parabolic shapes. Yeah, these would be provided on the test. Yep. Sectors of circles. Okay. So just go to D2L. I mean, you might want to just print that out and put it in your notebook. Here are two useful facts about calculating centroids. The first one is that in 2D, if, so a centroid always lies along any line of symmetry you can find. And so, for example, with a shape like this, this is a line of symmetry. And so without doing any calculations, you can figure out you know, you can find the coordinate, the x coordinate of the centroid. And then all you have to do is find up and down where the centroid lies. Okay. Also, if you can find two different lines of symmetry for any shape, wherever they intersect has to be the centroid. Okay. So if you can find two different lines of symmetry, the centroid lies at the intersection. So, what about the one we've been doing kind of intuitively up until now, talking about rectangular shaped beams? Well, this has two lines of symmetry. One that way, one that way. And so the centroid lies right in the middle, like we sort of intuitively know. A circle has infinitely many lines of symmetry, and they all intersect at the same place in the center. In 3D, it's similar. You can't, you don't deal with lines of symmetry in 3D, you deal with planes of symmetry. Go into your brain for a second and figure out how many planes of symmetry you would need to specify, fully specify a centroid in 3D. Shut your eyes, it helps. Three, that's right. So, in 3D, if you can find, well, the centroid lies on any plane of symmetry. And three planes of symmetry intersect at the centroid. Yeah, that's a good question. So I'm going to bring that up in just a second, but that has to do with the relationship. So we're talking about a geometric center, and we're going to use it in many cases to tell us where the mass center is, and that depends on that consistency of material that you're talking about. Okay, the second useful fact is you can break objects up into pieces and use a sum formula to calculate the centroid of the thing that's built up from all these simpler shapes. So this second useful fact is if you can break a body up into pieces with known centroids, you can use the sum formula to calculate the total centroid. And the sum formula looks like this. The total area times the centroid is equal to the sum over all the different pieces of the area of the individual piece times the centroid of the individual piece. And so, you know, notice that this is exactly the same form as the integral definition. It's just a finite sum instead of an infinite sum. In 3D, this says the volume times the centroid is equal to the sum over all the individual pieces of the individual volume times the individual centroid. So an example of when this would be useful is if you're trying to calculate the centroid of, you know, a shape like this. You wouldn't want to have to do this as an integral. That'd be a huge mess. But you know where the centroid is for rectangles, so you could just break it up into, you know, this many rectangles. You know the centroid of one is here, here, here. You can calculate the individual areas and just use that sum formula. One thing to keep in mind about this is that it works with subtraction too. So for example, if you have a rectangular shape that just has a hole out of it, you can use the sum formula using the whole rectangle and then subtract the area times the centroid of the circle, and that'll give you the centroid of the whole thing. So, for example, if this is the shape that you want, so you have a rectangular shape with a hole cut out of it. Then the total area times the centroid is equal to the area of the rectangle times the centroid of the rectangle minus the area of the circle times the centroid of the circle. Okay, so let me do one example here. So let's say that we want to calculate the centroid of this T-shaped thing. Let's say that the thickness here is 0.1 meters and the width of the top is that does not look right. Let me just change this drawing a little bit. Okay, so let's say that this is 0.1 meters. The width is 0.2 meters. let's say that this is 0.2 meters, and this is 0.05. And let's put the coordinate system here. And we want to calculate that centroid. Okay, well, right off the bat, you can notice that there's a line of symmetry like this. And so we already know that the centroid lies on the y-axis, okay? So the only thing we have to do is figure out the y position of the centroid. So line of symmetry says the x component of the centroid is equal to 0. So now for the y component, the total, let's break this up into a top rectangle and a bottom one. I'm going to call this one body 1 and this one body 2. So the area of body 1 is 0.2 times 0.05. So 0.01. The y component of the centroid of body 1 is 0.1 up because it's halfway up the height. So this is just going to be 0.1. The area of body 2 is 0.1 times 0.2. So 0.02. The y centroid of body 2 is, so from the origin, we'll go up 0.2 to get sort of to the bottom of this rectangle, and then we'll go up another 0.05 to get to the centroid. So 0.25. And so if you put that all together, the total area, 0.03, times the y centroid is equal to 0.01 times 0.1 plus 0.02 times 0.25. And so the y centroid is 0.2. And so the centroid is 0.2, and this is meters. Any questions about that? Okay, so I guess let's stop there. And so next time I'll talk about how to fit this into the two different things that we're going to do with this. One is using it to find where to apply the weight of objects, and the other one is to figure out how to deal with distributed loads, which means when forces aren't acting at a point, but they're spread out over some region. Okay.